Hello everyone, my name is Neil Jackson, and for the fifth lab I will be analyzing the motion of a falling slinky starting at static equilibrium. I'm going to be using the momentum principle to track the systems, which is my slinkies, momentum, velocity, acceleration, and position, and I'll be using the energy principle to compare the system's kinetic and gravitational potential energy. And understanding this system will help us in the fields of sports science. For instance, if you take a baseball and you hit it with the bat, you are only feeling the magnitude of the rebounded force off the ball. My system is the Slinky. Specifically, I will be analyzing the top of the Slinky's motion. My surroundings are the Earth. Here are my mass, spring constant, period, L naught, and force of gravity, or gravitational constant. And then I have the number of coils, radius, and total mass because I needed those to calculate some of these values. For finding K, I tried analyzing the system at static equilibrium at first, but I realized I don't have a tension, so that won't work. Then I tried looking at it from an energy perspective, realized I don't have a final velocity or h, so that wouldn't work. So by looking at the oscillations, I could work backwards and find K. Here's a picture of the tracker data I used to calculate the period. As you can see by this graph, our oscillations are slowly dampening down, meaning that there's some sort of dissipative force acting on the Slinky, let it be air resistance or a change in internal energy. Now, this was not taken into account when calculating the period, so that is something to keep in mind for the conclusion. Here is the tracker video I analyzed for my lab. This video was shot in slow motion, so I had to change the frame rate. As you can see by the graph, we started off with exponential decay and then transitioned into more of a linear decay, which was a little odd from gravity. However, the reasoning for this is probably due to some type of air resistance. Here's the code I used to run my model. This first part just details the generation of the graphs and spring. This is my initial conditions and the chunk of code that I used to import my CSV file, same as Lab5. This chunk is my initial calculations, such as L naught, K sub S, and G. In my while loop, I'm calculating F net, updating the momentum and position and acceleration in this case. I update my spring, calculate my new energies, and then I plot everything. And in this second while loop, I just have some code that goes into my CSV file and calculates my tracker data's velocity and acceleration and plots that as well. And I have an if statement that tells me to stop doing these calculations once the Slinky is fully compressed. So here is the program. This error message is just telling me that there's no Z in the CSV file, nothing to worry about there. The energy graph is what we expected, with delta E remaining constant at 0, delta K increasing linearly, with delta UG decreasing linearly. So our position versus time graph makes quite a lot of sense actually. We have our predicted motion in green, which makes sense, and we have the true motion from tracker in blue. It matches nicely up top, however, it quickly deviates from our predicted motion due to dissipative forces. And this is when things start to get a little weird. For our velocity versus time graph and our acceleration versus time graph, our predicted velocity is decreasing linearly, which makes sense as the derivative of an exponential function is a straight line. And then our acceleration is constant at 9.8, which also makes sense as the derivative of velocity is acceleration. However, when you compare that to our tracker data, you can see that things get quite weird. And it's not a coding issue, as this is exactly what I got from tracker. However, it's something curious to notice. Specifically in this velocity versus time graph, we can see that our velocity is slowly increasing towards 0, which would make sense if there is a drag force or other dissipative forces acting in our real-life system that wasn't modeled in our predicted model in GlowScript. Similarly, we can see this effect is true for our acceleration graph. To conclude, I would like to say how interesting it was to see how these external forces impacted my system. It's a great example of how static equilibrium works, and I'm happy to say that this experiment in this lab will help me in my later engineering courses. If I were to redo the experiment, I would definitely find a way to incorporate the dissipative forces that negatively impacted my model, such as drag. I think that would be a good place to start.